We've been working with Professor Drain and Professor Francis and Dr. Sad at Harvard College for these past 4 years at the chemistry department. And the title of my presentation is Porphyrins and Phthalocyanines as New Dyes for Solar Cells. So before I get started with porphyrins and phthalocyanines, those are words that you probably don't know about. Can anyone tell me what a solar cell is? Solar panels? Yeah. Okay, close. The solar cells, solar panels, photovoltaic cells, these are all the same things. They're just devices that collect sunlight and turn it into energy. Energy that we can use like electricity. So those calculators, they have that black little device that collects sunlight and turn it into energy. So that's what we were working with in Hunter. So this is a very simple diagram of what a solar cell looks like. There are many different types of solar cells. The ones that NASA uses are like $2 million and $2 billion each, and those are they're about like 60 to 30% efficient. But the solar cells that we want to work with are things that you and we can use. So these are cheaper and less efficient. They're about like 11% efficient, and this type of solar cell is called the Drexel type solar cell. Just like a battery, a solar cell has a cathode and an anode, and it has some kind of fluid, we call this electrolyte, that does oxidation redox reactions that keeps the whole circuit going. But unlike a battery, the anode or the cathode, one of those, is going to be transparent so that light can pass through. So in our case, it's a conducting glass. In a Drexel type solar cell, what we use is right after the anode, right after the conducting glass, we have injection of nanoparticles. In this case, it's titanium dioxide. On top of that titanium dioxide, we have a dye. A dye simply is anything that colors. That's the definition of the dye. It's an ink. But this dye is specialized. It is a dye that is photoconductive. What that means is that when you shine light onto this dye, it gets charged. Electrons inside the dye get charged, they get excited, and move on to the TiO2. And then you have a kind of like a circuit inside of the solar cell. So this works just like a battery, except this dye is getting charged through sunlight that comes through this glass and hitting this dye. But like I mentioned, we're working in the chemistry department, so we're not electrical engineers. We're not building these solar cells. What we're actually concerned with are the dye itself. We play around with chemicals. So we're making these dyes, and these dyes are either porphyrins and phthalocyanines. And that's where my title comes in. My title is Porphyrins and Phthalocyanines. So we're working with porphyrins and phthalocyanines as a dye to make solar cells. Porphyrins and phthalocyanines. These are dyes that do cool things when you shine light on them. So the idea is we're going to make a cheap solar cell that is about 11% efficient so that the general public can use. Because we're running out of fossil fuels, it's not economically feasible to use fossil fuels anymore, and it's not environmentally good either. So what happens is sunlight hits this dye. So this line here would be my dye, either porphyrin or phthalocyanine. Sunlight hits this dye, and the electrons inside of the dye gets excited. The electrons flow out of the dye into a metal, and the metal is conductive. And so the electrons flow out of the metal onto this plate, which is a nano TiO2 plate. TiO2 titanium dioxide plate. This acts as a semiconductor. And after that, you have your transparent glass, and then after that, the whole circuit of the other stuff that I showed you previously. So before I get into how this thing works, I want to talk to you about porphyrins. Porphyrins are four-sided organic complexes. They're found all over nature. Actually, this idea of using porphyrins for solar cells is stolen from plants. Plants have been using porphyrins in their chlorophyll for about billions of years. They use porphyrins. They use a magnesium-based porphyrin to capture sunlight and turn it into energy. We're doing almost the same thing. Other than just plants, we ourselves, we use porphyrin in our blood, in our hemoglobin, in our vitamins. Porphyrins are all over the place in biology. They're mainly known for their photoconductive properties, and that's why we're using them. Because when you shine light onto them, they do cool things. This is the porphyrin that I'm using. There are many different types of porphyrins out there. The porphyrin that I'm using is tetrophenylporphyrin, or TPP for short. And next, I'm going to introduce to you phthalocyanines. Phthalocyanines were discovered by accident. They are really used as dyes. They're not used like porphyrins, they're not used in our bodies as much. If you have anything that's blue, like jeans, anything that's purple, it probably has phthalocyanines in it. So phthalocyanines are used for other purposes than electrical purposes. But we're using phthalocyanines because when you shine light on phthalocyanines, just like porphyrin, the electrons inside of the phthalocyanines get excited to the next state. So the method that we're using is that we're going to take that TPP, our porphyrin, and we're going to put a metal inside, so a very cheap metal that's abundant on Earth. So either zirconium, hafnium, zinc, anything like that. We're going to put a metal inside of it, and then use that metal-laden porphyrin and put it onto the titanium dioxide. So that's the method that we're using for the porphyrins. For the phthalocyanines, it's a little different because porphyrins and phthalocyanines, although they look similar, the structures are different. This is what a porphyrin looks like. This is what a phthalocyanine looks like. They're a little different. So the idea is we're going to use a metal, we're going to start with the metal, and we're going to build the phthalocyanines around it. Whereas with the porphyrin, we took the porphyrin and we've inserted the metal inside of it. Here we're going to take the metal and we're going to build the phthalocyanine around it. So we're going to use dicyanobenzene, that's this. We're going to mix it with methyl naphthalene and trichlorobenzene. We're going to heat it up to very high temperatures, and we're going to start building this around the middle. So once you're done with your synthesis, in your test tube, you're going to have this stuff and a lot of other junk. So how do you separate the stuff that you want and the stuff that you don't want? What you do is you wash it. You wash it with toluene, you wash it with methanol, you wash it with other solvents that you can think of that will dissolve the stuff that you don't want and will keep the stuff that you do want. So we're washing it with toluene, we're washing it with methanol, we're washing it with DCM, we're washing it with methanol again, we're washing it with acetic acid. And what that does is it keeps our phthalocyanine and metal and washes out all the stuff that we don't want. Okay? So after you have that, you have a vial of nanopowders that's dark and colorful with the porphyrin of phthalocyanines that are metal in it. And let's say I come to you and say, okay, this is your porphyrin or phthalocyanine. How do I know? How do you know that that's porphyrin or metal or phthalocyanine? The way I prove that to you is I characterize it using UV vis. What this machine does is that you take your sample, you put it into the UV spectrometer, and it shoots UV light through your sample. And everything absorbs UV light. That's some wavelength, right? So we know for a fact through literature that porphyrins absorb UV light at 416-ish, and from 500 to all the way to like 800, they have little tiny clumps of absorbance. That's porphyrins that do not have metal. If you do have a metal, it will still absorb UV light at 416 nanometers, but also absorb UV light at 540. So if you see that, if you see this peak at 540, as well as the peak at 416, then you know that you have a metal-laden porphyrin. So that's how we can prove that we have metal-laden porphyrin inside of our vial. Phthalocyanines, we do the same thing. We put it inside UV stuff, And free-based phthalocyanine looks like this. And if you have metallated phthalocyanine, it looks like a blue one. At 680, you should have a very sharp peak. So that's how we prove that in our vial, this is actually metallated phthalocyanine. Or the previous slide, that was actually metallated porphyrin. Other than that, we can still have other junk inside of that vial of product, right? So, and we also don't know exactly how this thing looks like. All we know is that this is some powder, and it has metallated porphyrin or metallated phthalocyanine in it. We don't know how the phthalocyanine or porphyrin looks like. So what you do is you do other characterization tests, like NMR. NMR stands for nuclear magnetic resonance. So what this does is it tells you information about the bonds between your hydrogen atoms inside of your product and every other atom inside of your product. And using that information, so this is your information, all these peaks represent different hydrogen bonds in this complex. This is a porphyrin with the metal and then a compound. And using that data, you can come up with an estimated picture of how this thing looks like. So here, this is not a real picture. This is a computer drawn picture using this data. I have two different data because one is zirconium metal and one is hafnium metal. And I wanted to show you the difference between these two. This data is very clean. It doesn't have that many background noise. However, this data has little tiny background noise. So between these two data, this is a very clean data, this is not as clean. So you might ask, well, if porphyrin works, why phthalocyanine? Or if phthalocyanine works, why porphyrin? Why are we working with two different complexes? Why not just stick to one? Well, the sun gives out all types of light, right? That's why you see the rainbow. It has blue, violet, all the way up to red. It gives out all that light. It even gives out UV light and infrared light. So you want to capture all of that. Porphyrin only captures the light that's around 420 nanometers. That's violet, indigo, bluish light. Phthalocyanine, on the other hand, captures light that are reddish. So if you have a mixture of these two, then your solar cell will capture mostly all the light. And that's why we're using phthalocyanine and porphyrins. So in conclusion, this stuff works. We've been optimizing our methods for about 4 years, and the way we make metallated porphyrins, the way we make metallated phthalocyanines, and then putting them onto the TiO2 surface plates, it works. However, porphyrins are less stable than phthalocyanines, and we believe that's because phthalocyanines, the structure of the phthalocyanine is very stable. The way we make the phthalocyanine around the metal is a very stable methodology. So metallated phthalocyanines are more stable and a stronger dye than porphyrins, but both of these are very stable compared to other things that we've used. And the good thing about this is these are organic complexes. These are biodegradable complexes. And that's a very good plus when you're talking about green energy. These are just pictures of these things. Anything that's blue, anything that's red or pinkish are porphyrins and metallated porphyrins. Anything that's bluish are phthalocyanines or metallated phthalocyanines. And these are two examples of solar cells that we've made in our lab. This is a porphyrin solar cell, and this is a phthalocyanine solar cell. And currently we're working on mixing the two. We're working on mixing porphyrins and phthalocyanines and making solar cells that are some kind of a mixture of the two, so that it has a wider range of light capturing ability. Some of the references that we have. And finally, I want to acknowledge Professor Drain and Professor Francis for letting me use the labs. Of course, Dr. Sad and HCS, and all of my lab partners. These are my lab partners that I've worked with for 3 to 4 years. And our research is funded by National Science Foundation, and of course you guys, the listeners.